good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be talking about the momentum equations. So let us get started. So the topic for today's lecture will be as follows. We will first be revisiting the material derivative of integrals. Then we'll talk about the linear momentum principle and derive the equation of motion in the Eulerian form. And then we will go to the angular momentum principle and show the symmetry of the Cauchy stress tensor under accelerations as well. So let's begin the lecture. We talked about the material derivative of integrals when we started our discussion with balance laws. But in that discussion, we had talked about the intensive property being a property per unit volume. We will be revisiting that by discussing what happens when the intensive property is a property per unit mass. So we defined the material derivative of the extensive property P as the material derivative of the integral over the current volume omega of the corresponding intensive property, which is a function of small x and t. So that's the Eulerian description. So here this quantity was a property per unit volume. But now since we are interested to write this integral for a property per unit mass, so we can write P star, which is written per unit volume. So this can be written as A star, which is the corresponding property per unit mass times the density field. So with that, the material derivative of the extensive quantity P as a function of time can now be written as the material derivative still over omega of A star times the density times d omega. And now since we're interested to move this derivative on the right hand side inside the integral, so we express the integral in the reference configuration by writing the d omega element as j times d omega naught, and we also express A star in the Lagrangian description. So we have a tilde on top, and so is the density written in the Lagrangian description. And we still have a d by dt here. So now d by dt can easily move inside the integral. This becomes d by dt of the product of A tilde star rho tilde times j times d omega naught. So if we apply the product rule, this becomes the material derivative of A tilde star times rho tilde j plus A tilde star times the material derivative of rho tilde times j times the d omega naught. Now if you look at this term, if you recall the equation for the conservation of mass written in the Lagrangian form, this was 0. And that is how we'd express the Lagrangian form of the continuity of the mass conservation equation. So this is a 0. So we're basically left with integral over omega naught A tilde star ij, I'll write a dot on the top to denote material derivative, times rho tilde j times d omega naught. And j times d omega naught is a d omega. So we will transform everything back to the current configuration. So A tilde now becomes an A again, but it still has a dot on top, times a rho, and this was d by dt of the quantity Pij, which is the extensive quantity at a given time t. So we'll write this explicitly in terms of the functional dependence. This is small x and t, times rho, which is also a function of small x and t, times d omega. Let's write d by dt of the quantity here. So let's box this. And this is how we express the material derivative when quantities are written per unit mass. So basically what we notice is that this d by dt here simply goes into the A star quantity. So we will be using this today for writing the linear momentum principle. So let's move on to that. So linear momentum principle is used to get the equation of motion. So before we start writing this, let us specify the various terms that we'll be using. So first we have a current configuration, which is at some time t, and the volume of this body is omega. Now this could be a subset of the body, that is a subvolume, rather than this being the complete object. So the bounding surface of this is gamma, and then we'll have an infinitesimal volume element, which we'll denote by d omega. And similarly, we could have an infinitesimal area element, which is given as d gamma with an outward normal n hat. In terms of forces on this volume element, a body force rho bi is acting, and on the surface element there's a traction T for the area with an outward normal n hat vector. And this body as a whole is moving with a velocity field, which is given as v as a function of small x and t. So with this now we can write the equation. So the linear momentum principle is based on Newton's second law, which states that the time rate change of the linear momentum of a material particle is expressed as the sum of all the external forces acting on the particle. And this expression of the Newton's second law is more general than writing F equals ma, because this allows for the situations where the mass is changing over time. That is, we have an m dot term as well. So we will be sticking to this expression. Now, since we are interested to write the linear momentum principle for this body on the right hand side, which is a collection of some material particles, we basically will say that the d by dt of the sum of the momenta of all the particles is equal to the net external force acting on the particles. And this is something we know from mechanics, because the internal forces get cancelled. It's only the external forces that contribute to the rate of change of the linear momentum of the system. So the left hand side becomes d by dt of the integral over the complete volume of the infinitesimal momentum. Now dp can be written as dm, which is the mass of the infinitesimal volume, times the velocity field, and dm can be written as a density times d omega. So this is the left hand side. And on the right hand side, since we categorize all the forces into body and surface forces, so first we write the contribution of F external from the body forces. So we integrate over the complete volume to add all the body forces, and then we say rho times bi, which is the body force per unit volume, times d omega. And then we have the integral for the surface forces on the bounding surface of this volume. So this will be a closed integral, and the surface force from Cauchy stress principle is simply the traction over an infinitesimal surface with an outward normal n hat times d gamma, and this is a vector, so it's an index I. So we'll number these terms as 1, 2, and 3 because we'll be handling them separately now. So let us consider the first term. We have d by dt of integral rho vi d omega over the current volume omega. Now if you see, this is like our quantity A star, where Vi is the intensive quantity per unit mass. So this is like our A star. So this becomes integral over omega rho times Vi dot times d omega. Now the term 2 stays as it is, so we'll discuss the term 3 now. So term 3 is a surface integral. I should write it's a surface integral over gamma of the traction vector Tn hat times d gamma, which is the infinitesimal surface force acting on the surface d gamma. So I can write this in terms of the stress tensor sigma using the Cauchy stress formula. So this becomes sigma ji and j times d gamma, and this can further be converted to a volume integral using the Gauss's theorem. So this becomes sigma ji comma j times d omega. So we have these simplified expressions. So let us put them back into the main equation. So we have an integral over omega rho vi dot d omega, that's equal to the body force term. So that was rho bi times d omega plus the third term, which is sigma ji comma j times d omega. So since all the integrals are over volume, so we can club all the terms together. So this becomes integral over omega rho vi dot minus rho bi minus sigma ji comma j times d omega is 0. And since our choice of omega was arbitrary, the integrand becomes 0. Or we can write, so this we'll call A, and this is the local equation of motion expressed in the Eulerian form. Now in this equation, if Vi dot, that is acceleration field, is 0, then we have an equilibrium situation. And we already discussed the equilibrium equations earlier, which we can get from this general equation A by putting the left hand side equal to 0. So from the linear momentum principle, we were able to get the local equations of motion written in the Eulerian form. Now let us move on to applying the angular momentum principle and see what we get. The angular momentum principle says that the time rate change of the vector L, which is the angular momentum of a particle. Now angular momentum is always defined about a point. So let's say we define it about a point O. So this L is an angular momentum about point O. So the angular momentum principle says that dl naught by dt is equal to the net torque acting about the point O, which is basically the net moment of all the forces acting about the point O, and these forces are the forces acting on the object or the material particle. Of course, in writing this, we are assuming that there are no concentrated moments acting on the body. So this torque is simply a torque because of all the body and the surface forces acting on the object, and does not contain the contribution of concentrated moments about the point O. And this absence of concentrated moments basically means that we're talking about non-polar materials. So let us say this is our object in the current configuration at time t, and this is our origin with the coordinate system Ox1, x2, x3, and let's say we have an infinitesimal volume d omega which has a velocity, let's say vi. So with this position coordinate, I can write the angular momentum about the point O for this particle contained in the infinitesimal volume d omega as small x cross the linear momentum of the particle in d omega, or this can be written as rho d omega times vi. So rho d omega is the dm times vi is the infinitesimal linear momentum. So let us express the angular momentum principle in our integral form. Again, from mechanics, we know that if we have a collection of particles, we can write the time rate change of the angular momentum of the complete collection of particles as the net torque of all the forces acting about the point O. So this becomes d by dt of the integral of the angular momenta. So the cross product here can be written as epsilon ijk xj times rho vk times d omega. So this complete is our infinitesimal linear momentum. And this is equal to the sum of the moments because of body and surface forces. So first we'll write the body force contribution. So this is integral over omega, and the moment of a force is simply x cross the force. So again we have epsilon ijk xj, and this time the force is a body force, rho bk times d omega. And then we have the contribution from the surface forces. So that's an integral over the complete bounding surface. That's again the cross product between the position vector and this time the traction acting on the area n hat times t gamma, and we have an index k here. So again we'll call these terms as 1, 2 and 3. So we'll simplify the terms separately and then combine all of them. So let's look at the first term. This is like our A star, which is the quantity per unit mass. So this derivative goes inside and we get a d by dt of epsilon ijk xj vk times rho d omega. Epsilon is a constant. We can write it like this. And then we have a d by dt of xj vk. So that becomes xj dot vk plus xj times vk dot times rho d omega. So we can expand this as epsilon ijk, and this xj dot is basically a vj vk times rho d omega plus epsilon ijk xj vk dot rho d omega. Now if you look at this term on the left, this vj vk is a symmetric second order tensor, and this epsilon ijk is a skew symmetric second order tensor. And we know that a symmetric times skew symmetric is a 0, so this becomes 0. So all we are left with is the second term, epsilon ijk xj vk dot rho d omega. So let's underline this, as we'll be substituting this later in the complete equation. Now we look at the third term, because we'll not touch the second term. So this was the surface integral epsilon ijk xj, the traction vector t n hat k times d gamma. So first we'll apply the Cauchy stress formula. So we can write the traction in terms of sigma, let's say q k nq d gamma. And then we apply the Gauss divergence theorem. This becomes an integral over volume epsilon ijk xj sigma qk whole differentiated with respect to del xq. Now again, epsilon is a constant, so this can be taken out, and then we have a derivative, so we can apply product rule. So this becomes xj sigma qk comma q plus xj comma q times sigma qk times d omega. Now this xj comma q is a delta jq. So this further simplifies. This is jq. So this further simplifies to sigma jk d omega. So now we'll combine the simplified expressions for 1 and 3 into the main equation for angular momentum principle. And since all of the terms are volume integrals, we'll combine them into one integral. So the angular momentum principle now states that the integral over the volume omega the integral of this quantity is a 0. So we moved all the term to one side. Now what we can do is we can take the epsilon common from all the terms, and then we have an xj in these three terms. So we can take an xj common and write rho times vk dot minus rho times bk minus sigma qk comma k, and then we have this term minus sigma jk times d omega, and that's a 0. And now if you look at this term, you will recall that this was 0 because this is the equation of motion, so this becomes 0. So this now simplifies to integral over omega epsilon ijk times sigma jk d omega is a 0. And since the choice of omega is arbitrary, we can write epsilon ijk sigma jk is a 0. Now if you recall that we had gotten the same expression when we had applied the angular momentum principle to equilibrium situations, and this had resulted in the fact that sigma is symmetric. So we have concluded that again, but this time for situations where the body may not be in equilibrium, that is, it may be accelerating. So the Cauchy stress tensor is always symmetric, of course, for non-polar materials. For polar materials, it may not be symmetric because we have some concentrated moments as well, which contribute to the angular momentum equation. So this brings us to the end of this lecture, where we applied the linear and the angular momentum principles to derive the equation of motion in the Eulerian form and to conclude that the Cauchy stress tensor is symmetric. In the next lecture, we will apply the linear and the angular momentum principles for Lagrangian forms. This will help us derive the Lagrangian form of the equation of motion, and through this we will also introduce two new stress tensors, which are the Piola-Kirchhoff 1 and 2 stress tensors. So Cauchy stress tensor is not the only stress tensor, we have others as well. So thank you very much, and I will see you in the next lecture.